Bragg, CDI, ptychography, tomography, and more, and also has been working more towards conducting multimodal and multi-scale microscopic studies on functional materials. So with that, take it away.
Thank you very much for the introduction. Good afternoon, everyone. I'm Xiaojing Huang from NSLS-II. At the beginning, I want to thank the organizers for arranging this workshop. And it's a great pleasure for me to come back. I was collecting experimental data for my PhD degree project like 15 years ago, and visiting back brought a lot of memories back. And in today's presentation, I'm going to talk about high resolution correlative imaging with coherent X-rays. This is the outline of my talk. I'll start with a brief introduction to the multimodal scanning probe microscopy, and then I'll show two attempts to solve challenges in coherent X-ray imaging. One is how to extend the depth of field. The other one is how to enhance a fluorescence image quality close to the ptychography images. Most of the work I'm going to present is done at the hard X-ray nanoprobe beamline at NSLS-II. The main idea of the beamline is focus X-ray to a tiny spot, and in order to achieve the diffraction limit beam, as already mentioned by the previous speakers, we need to select the coherent part of the beam. But to do that, we use a mono to select the temporary coherent beam, and then we use a secondary source aperture, basically a slit, to select the spatially coherent beam. And so far, the smallest beam size we can create is about 11 nanometer. And we scan a sample across that tiny focus beam, and at each scan position, we collect as many signals as we can. So far, we can run 3 detectors simultaneously that include a fluorescent detector and 2 pixel area detectors, one for transmitted scattering, another one for Bragg diffraction. And the photo on the left side shows how the detectors are oriented as like a kung fu pose for one experiment. So this movie shows a typical measurement with all 3 detectors running. The first panel is the intensity summation on the certain fluorescence peak. And the second panel is the transmitted scattering pattern. If we plot the integration of the transmitted signal, we can obtain the absorption contrast image. And if we analyze how much this pattern jitters in X and Y direction, we can obtain a differential phase contrast image. And the third panel is the Bragg diffraction pattern. And again, if we plot the integrated Bragg diffraction intensity, we can obtain a diffraction contrast image. We can further run spectral fitting to obtain the elemental distribution for each single components in the sample. And with using the transmitted scattering pattern, we can reconstruct a phase contrast image using either DPC or ptychography reconstruction algorithms. And by tracking the Bragg peak at each scan position, we can obtain 3 maps representing the lattice distortion. And we can obtain all this information simultaneously. And this is our version of multimodal imaging. With the nanofocus beam, we started a widely used lithium ion battery cathode material system, lithium cobalt oxide. One issue for this system is how to stabilize the layered lattice structure. One of our collaborators, they created a co-doped system. It's an LCO system co-doped with titanium, magnesium, and aluminum. And we collected 3D fluorescent signal from a secondary particle, and we found aluminum is almost uniformly distributed inside the particle. And on the other hand, the titanium, they create an interconnected network covering the particle surface and filling the gap between primary particles. So this interconnected network modifies the surface property and promotes the electrochemical reaction performance of the system. And we also did a 3D measurement from one single primary particle from the same for the same system, and we observed very similar behavior. The titanium tends to concentrate on the particle surface. And in order to investigate what's the impact of doping brought to the crystal lattice, we performed a nano diffraction measurement from the same primary particle. For this measurement, the 1 pixel area detector was oriented to catch the 101 bright peak, and the sample was rocked between ±1 degree angular range and with 0.1 degree angular step sizes. At each rocking angle, we did a 2D raster scan. And this movie shows the diffraction contrast image through the rocking curve, and we found the tons of features inside this primary particle. So through this rocking curve nanodiffraction measurement, at each scan position, we collected 3D diffraction data set, and we can track the center of mass of this 3D diffraction pattern, and then we can decompose the peak center along 3 specific directions. And we chose those 3 directions to give, because each direction gives a specific physics meaning. For example, one direction is perpendicular to the powder ring direction. That tells us how the D spacing changed from point to point. Another direction is along the powder ring direction, and that tells us how the lattice is deformed along this z-axis. And the third one is direction perpendicular to the powder ring direction, and that tells us how the lattice will deformed in another require the y direction, just the vertical direction in this case. So by tracking the center of mass of the 3D diffraction peak, we can obtain one D spacing map and 2 lattice bending map from this single crystal sample. And we compared the result from a bared LCO without doping, and we noticed this doping process actually adds quite a lot of more distortion to the sample system. And our colleagues did in situ powder diffraction measurement, and they found those preload strain field actually suppresses some undesired phase transition during cycling, and that also helps to promote the electrochemical performance. And this result suggests that the strain engineering could be another parameter to optimize the performance of this cathode material system. Okay, now let's shift the gear a little bit to look at the imaging system itself. So when we are pursuing higher spatial resolution, or we try to focus the X-ray to a smaller point, we are facing the similar challenges as the electron microscopy facility has experienced. One of the issues is that the depth of field shrinks aggressively for higher resolution. Iterative way to understand this effect is that the scattering signal expands over a evosphere surface. But usually, we perform the measurement with a flat detector. So when we are collecting high Q signal to achieve higher resolution, the flat detector deviates from the evosphere further away, and that blurs the features outside the depth of field range. And so in theory, the depth of field scales with the target resolution square over a lambda, and depends what criterion you're using. This scaling factor can vary from 0.5 to 5.2, but nevertheless, the depth of field will shrink quadratically with the target resolution. Before we go further, I want to emphasize that for diffraction-based imaging techniques, there's a subtle difference between depth of field and depth of focus. Because in diffraction-based imaging techniques, we try to use the signals outside the central divergence cone to achieve higher spatial resolution. So those areas corresponding to a larger numerical aperture, and that gives a natural depth of field smaller than the depth of focus of the native focusing optics. Okay, now the question we asked is, can we extend the depth of field while without sacrificing the spatial resolution? So we want to achieve higher resolution. So we want to still work with imaging system with large numerical aperture. We explored two methods trying to extend the depth of field. The first method is called multi-slice ptychography. This method is able to reconstruct planes at a different depths simultaneously. The second approach we tried is called focus stacking. Conventionally, this method takes a series of images while translating the sample along the beam direction, and then try to extract the in-focus features at the different exposures and stick them together. We extend this method, and we show we can replace the physical translation with numerical sectioning. So for the first method, multi-slice ptychography, actually, this method adapts the multi-slice concept developed in from electron microscopy community. So in this method, it decomposes a 6 sample into a series of thin layers, and each layer is thin enough so we can project all the features on that layer to a single frame, and then that frame will interact with the incoming beam. And then there will be a free space propagation between layers. And then if we model the interaction using this way, the X-ray wavefront will capture all the information on every slice, and then those information can be used to reconstruct the features on each depth. So this idea was firstly demonstrated in visible light regime. We applied this idea into X-ray regime. We collected one ptychography data set using a multi-layer Lowry lens focusing optics. Those two sample layers, they are separated by 10 micron along the beam direction. And this 10 micron separation is far beyond the depth of focus of the optics system we use for this measurement. And using the multi-slice ptychography algorithm, we can reconstruct the two planes with sub-10 nanometer resolution. And although the image looks pretty good, but if we look at the obtained image carefully, we can see there are some we call it ghost features representing the shape and the size of the crystal and showing on the wrong slide, on the wrong plane. And this is because those features represents the low spatial frequency feature. And this low spatial frequency feature, they don't propagate, they don't change much when we propagate within relatively short distance. So the algorithm couldn't distinguish them and separate them from different planes. Once we noticed that's the issue, and we realized, fortunately, in our multimodal measurement, we collected fluorescence signal of the sample. And this fluorescence signal can provide those low spatial frequency signals, which can be used to decouple those cross-talking features. So we apply this idea. We successfly reconstructed the two planes separated only by 500 nanometer in the along the actual direction by using the spatial frequency signal from the fluorescence measurement. The second approach we tried is focus stacking. This method also has been explored in both electron and X-ray microscopy communities. The basic idea of for this method is we took a series of pictures while translating the sample along the beam direction, and the features at different depths, they will show sharply at different frames. Then we need to find a way to extract those in focus features from different frames and then stack them together so we can create image with extended depth of field. Through simulation, we found ptychography actually can do this focus stacking numerically. So I took two images of flowers and separate them by distance, and then I illuminate these two planes using a focused beam, and then using this model, I simulate the one ptychography data set, and then for reconstruction, the first try, if I use the probe function on the first plane, and then we can see the reconstructed image shows the flower on the first plane reconstruct sharply, and the second plane flower is blurry. And then if I take the same data set and use the wavefront on the second plane for reconstruction, and we can see that now the flower on the second plane is sharply reconstructed, and the first plane is blurry. So this simulation tells us the wavefront profile determines which plane we are reconstructing. Actually, this effect is known as the propagation uncertainty in coherent diffraction imaging techniques. And this is because when the X-ray wave propagates from the sample to the detector, all the wavefronts at all the propagation planes, they give the same diffraction pattern. Those wavefronts, they are all allowable for this phase retrieval problem. But it has been pointed out that if we can apply a support constraint or phase constraint in the real space, it can break down this propagation uncertainty and determines which plane we are reconstructing. And so this simulation just shows us the probe wavefront can select the reconstruction plane in the same manner. So using the experimental data, we can clearly show this effect. For example, if we use the wavefront on the front plane for reconstruction, we can see the gold particles on the front plane is sharply reconstructed. And if we take this probe and propagate 10 micron to the real plane and use the same data set and do the reconstruction again, you can see in this case, the nickel oxide particle on the real plane was sharply reconstructed. So, and then the next step is extract those in focus features and stack them together to form a image with extended depth of field. So to do this job, we use wavelet transform. Compare with Fourier transform, the wavelet transform not only tell us which signal is significant, it also tells us where this signal coming from. So we start with the series of reconstructions at different propagated wavefront functions, and then we apply the wavelet transform to each of these reconstructed image. So we can create a stack of those wavelet transforms. And then at each pixel, we go through the stack and we pick up the maximum pixel value. And then we do this for each single pixel, and each pixel goes through the stack and grab the maximum pixel value. And then by doing this, we can compress this image stack into a single frame with each pixel has the maximum pixel value through the stack. And then we can apply an inverse wavelet transform together to obtain the real space image with features at different depths sharply presented. So this is our second way to extend the depth of field. Okay, now for another challenge for our multimodal imaging is that the obtained fluorescence image is usually has poor quality compared with ptychography, and this is because the fluorescence measurement image quality is determined by the probe size and the scanning step sizes. So in a simple way, the fluorescence measurement can be modeled as an integration of the illuminated sample area, and it's clearly this integration will have a limitation on the beam size, and also has determined by the scanning steps we're using for this measurement process. On the other hand, if we know how the wavefront looks like, for example, from ptychography reconstruction, and we know physically how the measurement was done, we know exactly the spacing of the steps, we can apply a deconvolution process to restore the fluorescence image. And this idea was proposed in 2012. They took this is the initial fluorescence image. They run ptychography reconstruction, obtained the probe function, and used probe function as the deconvolution kernel. And they do iterative deconvolution, and they can improve the fluorescence image quality. However, this deconvolution process is very sensitive to the noise level and other imperfections of the measurement. In the meantime, recently we learned that the neural network is very good at conducting convolution and deconvolution calculations. That inspires us to look for the machine learning solutions for this problem. So here we focus on the fly scan data position. So the difference is we need to add a continuous sample motion in this signal modeling process. So by adding this continuous sample motion, we take from a high resolution image, we can simulate the associated low resolution image, and we can simulate thousands of those image pairs. And then my colleague Long, he designed a network to learn the relationship between this high and the low resolution image pairs. And once we have this network trained, we can fit in the network low resolution image, and it's able to recover the high resolution image. And we simulate the two cases with two different probes focused by a Frañó zone plate and by a multi-layer Lowy lens. And the simulation shows the network works pretty well. And I have to say here, this network is trained for one specific experimental condition. So let's say if you do another measurement with a different probe or using different scan steps, this network needs to be retrained for this new condition. Okay, and then using this trained network, we enhance the 2D fluorescence projection image first, and then we do 3D reconstruction using the enhanced images. And then we can see we can obtain the enhanced fluorescence image with a quality improved quite a lot from the initial fluorescence image in both zone plate and the multi-layer Lowy lens cases. And those newly resolved features show very good consistency with ptychography reconstruction, and this gives us a confidence. Because if we look at the raw and enhanced, I barely see those fingers here, but it's clearly show there. And then we are questioning whether can we trust those newly resolved features. And then fortunately we have ptychography reconstruction to provide a high resolution image, and then the consistency between them, those two approaches give us confidence this network is doing the job correctly. And besides the nice looking images, we also care whether the quantitative information is preserved in this resolution enhancement process. To check that, we applied the enhancement into the three major elements into this sample system: nickel, manganese, and the cobalt. And we checked the composition concentration before and after this enhancement, and we found this this ratio is preserved quite well in this process. And this sample we measured actually has a manganese-rich share. And from the raw fluorescence image, we can clearly see this core share structure. But with the enhanced image, we can see the resolved fine cracks on the particle. And if you look carefully, those manganese-rich area actually propagates inside the particle along those exposed crack surfaces. And some of them reach to the central void inside this secondary particle. And those new knowledge cannot be seen in the initial fluorescence image. And this we are very happy to see like this improved spatial resolution actually brings a new knowledge to the sample system to help us to understand the sample system. And so far we only enhanced the 2D sampling of the fluorescence images. The next step, we're trying to enhance the 3D sampling by adding more projection angles into the fluorescence image. For this task, we defined a new network using this dual branch structure. This dual branch structure can extract and process features with different sizes separately. And then after we trained the network using this dual branch network, and then we refine this trained network using a small amount of experimental data set. So those experimental data set are the repeated measurement of the same sample with coarse and fine scanning steps. So those provide the coarse and low and high resolution image pairs to fit into the pre-trained network to do some refinement. And we found those after refinement, they can some artifacts introduced by the enhancement process can be removed by this refinement process. And for 3D sampling enhancement, we start with initial 3D reconstruction using 71 projections, fluorescence projections. And then from this preliminary 3D reconstruction, we can reprojected 271 projections. And then we use the pre-trained and refined network to enhance those 271 projections. And then using this enhanced projections, we can obtain a better reconstruction. So the image on the right side shows that the initial 3D reconstruction gives a spatial resolution about 61 nanometer. And then if we only do the 2D enhancement, we only enhance the 2D projections, and then we do 3D reconstruction, it can improve the resolution down to about 21 nanometer. And now if we adding more projections into the process and also enhance the resolution of the newly projected projections, we can further push the resolution down to about 15 nanometer. And we also try to adding more projections into this data set. And we noticed the improvement of the resolution almost flattened out after 271 projections. Adding more projections doesn't seem to improve further. So it seems like we are hitting now at the stage, we are hitting the bottleneck of the 2D sampling already. So for the 2D enhancement process, because we used the ptychography reconstructed probe function as the kernel. So the ultimate pixel size in the enhanced fluorescence image should match with the ptychography reconstruction pixel size. So let's say in this case, think it's the ptychography reconstruction pixel size is about 7.5 nanometer pixel size. And then here you can see that we already obtained the 3D spatial resolution doubles the pixel size. That's pretty much already we're hitting the limit already. Okay. In summary, we're trying to show you the multimodal scanning probe microscopy is a powerful imaging method. It can give you structure, elemental, and strain information from the sample simultaneously. And we showed you our attempts to solve two challenges in high resolution imaging. One is extending the depth of field without sacrificing the resolution. Another one is we're trying to use machine learning methods to enhance the fluorescence image. And with that, I want to thank all my collaborators and the colleagues. And before I end the talk, I want to let you know now we have two beamline scientist positions available at the imaging program at NSLS-II. But those two beamlines, both of them are scanning probe beamlines. One is a nanoprobe, one is a submicron probe. And if you know a good potential candidates, please help us to distribute these links. And thank you very much for your attention.
Right, thank you very much. Maybe we have time for a quick question or two. We'll start with Devin.
When you're doing your wavelet transformations, what wavelet do you end up choosing? Because the shape of the wavelet is the wavelet coefficients that get out end up being quite sensitive to the shape of the wavelet you choose.
Right. That's a very good question. I don't have the answer in my mind. If you don't mind, I would refer you to this paper. But I do remember we do try. There are a few wavelet transform packages available, and we tried all of them. And there's one works specifically better than others. I forgot the name. It's like complex value something. So it's been a while, so I don't remember. So yeah, you are right. So how to do this wavelet transform makes difference, and we explore the available methods and pick we found one of them works the best.
Thank you. I think we'll do one last question. Yes.
Taking the X-ray as the source of light, how it differs from the other cutting-edge microscopy, like from focal optical division or two-photon to photon, because they also have depth and also and stacking features. So how it adds a differentiation to the existing image.
If I understand correctly, you're talking about the depth of field.
Other technologies like Ophus, division, two-photon, and two-photon. So how it is different from that microscope?
I would say we apply different physics principles to I would say because in this method specifically, this focus stacking, I think the overlapping constraint provided by ptychography gives us the opportunity to realize this numerical stacking. We don't need to take extra data set. We don't need to translate the sample. Using the same single data set, we can do numerical sectioning. I think that's one from us. That's one of the clear advantage given this method.
Right, let's thank Xiaojing one more time.